Okay, picking back up from where we left off yesterday. Problem 3.1 here says, suppose the warehouse were laid out so that there were 15 paths from A to B and 12 paths from B to C. How would your answers to parts B through F of problem 3.1 change? Got a little model here that shows here's checkpoint A, checkpoint B, checkpoint C. This indicates there are 15 paths between A and B, 12 paths between B and C. First question asked, how many paths are there from A to C going through B? Well, we decided yesterday this was just another version of the counting principle. And we decided since there were 15 different paths that you could take from A to B, 12 different paths you could take B to C, then you can multiply those choices, and 180 would be the total amount of different possibilities for paths that you could have from A to C going through B. Question C says if Rodney has a small locker, how many of the paths from A to C pass by his locker? Well, like we decided yesterday, if we're going to say he has a small locker, we're really limiting the possibilities that the guard could walk down from A to B. So instead of 15, we're making that choice of 1, because it has to be the one that goes by his locker. The large lockers still finish out the same way. There's still 12 possibilities there, so your grand total here is 12. D says if Rodney has a large locker, how many of the paths from A to C pass by his locker? Similar to the previous case, but in this one we're limiting the paths that the guard could take from B to C. So the guard could take 15 different paths from A to B, 1 path from B to C, and so we get 15. The next question asked, if Rodney has a small locker, what's the probability that the guard will not pass his locker on one of her rounds? Again, the probability being the successes over the total. It's a shorter way of saying that. We decided yesterday that we really didn't need to consider the second path. So if Rodney has a small locker right here, then the total path that can go down the small locker row would be 15. And we have to figure out then how many do not pass by his locker. And of course there's only one that passes by his locker, so how many do not would be 14. So there's a 14 out of 15 probability that the guard will not pass by that particular locker. Question F asked the same thing about the large lockers, and here you are, here's the paths with the large, and just like in the previous problem, we really don't even need to consider the small lockers. So our success is over our total. There are 12 different paths. How many of them will not pass by his? Will be 11. So there's the probability that the guard will not pass by his locker is 11/12. We're going to skip ahead here a little bit and look at networking models. This diagram below is a model of the floor plan of the warehouse. It's a diagram like this is called a network. A network is made up of nodes and edges. And this one below, the nodes A, B, and C represent the warehouse checkpoints. And the edges connecting the nodes represent the aisles between the rows of lockers. If you remember from checkpoint A to checkpoint B, there were 9 paths. So 1, 2, 3, 4, 5, 6, 7, 8, 9. These edges all represent the paths from A to B. A path from node A to node C consists of an edge from node A to node B, followed by an edge from node B to node C. This network models the warehouse floor plan because it contains all the important information in a simplified form. You won't see any lockers here, but the actual lockers themselves, if you remember, weren't really that important. So let's look at problem 3.2. In this network, a single edge connects node A to node B, and 8 edges, you could count them 1, 2, 3, 4, 5, 6, 7, 8, connect node B to node C. How many paths are there from node A to node C that pass through node B? Think about that for a second. Try to work that out. Pause this, and when you get an answer, you can restart. Well, you can see if you just simply count paths, here's 1, here's 2, 3, 4, 5, 6, 7, and 8. So there are a total of 8 paths that go from node A to node C going through node B. Next question. In this network, 2 edges connect node A to node B, and 5 edges connect node B to node C. How many paths are there from node A to node C that pass through node B? Try that one, and then pause when you unpause when you think you have the answer. This one's definitely going to be harder just to count. Not impossible, but a little bit harder. So if we look back up to A, we can see again the counting principles show up here, or the paths that we took. There was one choice from A to B, and then 8 choices from B to C. And we got 8. Isn't that just the product of one pathway times 8 pathways? So in number 2, we could look here and we could just see, all right, how many choices do we have to go from A to B? Obviously, there's 2. How many pathways from B to C? 1, 2, 3, 4, 5. So using the counting principle, 2 times 5 reveals that there are 10 different pathways that go from A to C all the way through B. That's certainly going to help us out in question C, where we say in another network there are 25 edges connecting node A to node B and 32 edges connecting node B to node C. That would take a long time to follow down each single individual pathway. Luckily, we know it's just the product of the choices we have at each category, or at each node in this case. $25 different choices to take at the first pathway, 32 in the second pathway, 800. Counting principle makes things a lot simpler and easier to do in that case. Problem 3.2 follow-up question 1 says for each network in problem 3.2, find the number of different round trips from node A to node C and back to node A. So again, a round trip would start at A, go through B, then go to C, then back to B, and then to A. So I want you to think about this. How many different round trips could be made on this network? Unpause when you think you have your answer. The most common mistake to make here is thinking, well, if there were 8 paths from A to C, then if I'm coming back, all I have to do is double that. 8 and 8 would be 16. Sounds reasonable, but it's just not right. What you really have to think of this as, just like we've been thinking, as choices with pathways. From A to B, there's one choice. From B to C, in this one, there are 8 choices. From C going back towards B, there are 8 choices. Then from B back to A, there's one choice again, which tells us it's a far cry from 16. 1 times 8 times 8 times 1 is 64.